tight. I wish I could almost like clip it on, you know?
Right.
I can see that. Cool, guys. While everyone gets settled, just go ahead and see if you can guess, what elevation are we sitting at today? That's what today's webinar is about. We're going to be talking about how elevation influences an ecosystem. All right, just hang tight. We've got another 7 minutes and we'll get going. Man, you can see forever. All right, guys, we got 5 minutes till we start. I'm going to give you guys a little view of what we're looking at today, maybe help you guess. right, got a couple more minutes. Let's get settled here. 4 more and we will get going. But while we're waiting, see if you can figure it out. Get going. Guys, we're almost there. Just anybody that hasn't entered their guess yet, try to guess what elevation are we sitting at right now. We're going to use that number and focus on what it does to the ecosystem up here where I'm sitting at. Alrighty. Alright everyone, hello, my name is Tom Olson. It is 4 o'clock and we are about to start on our second virtual adventure. This one's called Going Up. It's elevation and ecosystems. How does elevation influence an ecosystem? Well, it turns out it has a huge effect, actually. It also depends on several other things. During our last webinar, we talked about aspect. And now aspect is talking about the orientation of a slope in relationship to the sun. So here at elevation, that aspect becomes even more important. We're going to be going over several different topics throughout this, and there's going to be different opportunities for you to participate. I would love it if you could enter something into the chat too when I ask some questions. It'll allow me to interact with you a little bit. Okay, so I was asking, how high up are we? I got one guess. We're looking at 12,000 feet. That's pretty lofty. We're not quite up there. Right now, we're at about 10,300 feet, okay? I wanted to get you guys just above 10,000 feet so we could talk about a few certain things. This is really where things start to get a little bit weird, okay? Now, one thing I want to say is that there's two different things when we're talking about elevation. Elevation really just talks about the summit of a peak in relationship to it and to sea level. But there's a second thing that a lot of people don't think about when it comes to elevation. Do you guys know what that is? It's prominence. Prominence talks about how high a peak is from the lowest area that you can see the peak, or a lot of times from your vantage point. So for example, I want to show you guys out here to the view to the west, or to the east. If we look out this way, and you can see way out in the distance, way out there, that's about the lowest place you can see this peak from. Now, I'm at 10,000 feet right now, but that lowland down there is about 7,000 feet. So really, this peak only has 3,000 feet of prominence. Now, the reason I chose this mountain too is because this mountain's the same elevation as San Antonio and the San Gabriel Mountains. Now, a lot of folks in LA are right next to the ocean, okay? So you go ocean level to 10,000 feet, that is massive. That's a 10,000 foot prominence. That's unheard of, it's massive. Seriously, that doesn't happen many places. Versus here, when I'm on a 10,000 foot peak and we have a 3,000 foot prominence, much more common. So, as you guys see the infographic, that might help you understand a little bit, okay? So prominence is the vertical rise of a peak relative to a vantage point. So say this valley right here, which is where we might be at out there, if this peak is at 9,500 feet, what is the prominence for that peak? Well, it'd be 9,500 minus 2,500, that's the point I put here. So we're looking at a 7,000 foot prominence. Versus here, if I'm down here at sea level, for example, and I come clear up to 8,000 feet, I'm looking at an 8,000 foot prominence. So even though this peak is only 8,000 feet, this one's 9,500, it's 1,500 feet higher, this one has more prominence. Now, why does prominence matter? Prominence really matters because that's what's going to tell you the difference typically in temperature between where you are and where the peak is. Because if you're not at sea level and you can't get the temperature at sea level, it's difficult for you to guesstimate how high up that location is going to be and what the temperature is going to be at that location. So if we're going to look at our pre-worksheet, our pre-activity worksheet, we looked at our elevation and then we looked at the summit of San Antonio. And now it turns out that for about every 1,000 feet you go up, you drop about 5.5 degrees Fahrenheit. Or for the metric minded, if you go up 100 meters, you're going to drop 1 degree Celsius. Okay, so that's a great estimation. So let's take the example from the pre-activity. We were looking at sea level to the summit of San Antonio, it's about 10,000 feet. So for every 1,000 feet we go, we're looking at 5.5 degrees. So on average, you might guess that the summit of San Antonio is roughly 55 degrees colder than sea level. Now, that's a complete estimation. I don't think you should stick to that. It's definitely not always accurate, but it will give you a good idea when you are planning and trying to prepare for your adventure up in the mountains. You need to know what you're up against, particularly when it comes to the exposure that you can experience on a summit. All right. I'm going to pause just for a second, just make sure that our feed is still going through. As I just said. Seems like I lost. Okay, for some reason, I'm just going to put something into the chat, see if anyone can respond to me. Just want to make sure that the chat is working so we can talk with each other. Not getting any feedback. I hope you guys aren't disconnected right now. Give me 1 second, guys. Okay. Perfect. Well, people are telling me it's still going through, so we're rolling with it. Alrighty. So, we're talking about being clear up at 10,000 feet, so we can compare the location I'm at to San Antonio. Now, what happens when we're thinking about the air surrounding the peak? What happens when air is heated? what happens to it? Think about it. What if you put a water bottle in your car and your car heats up? Typically, when you crack the top of that water bottle, air is going to come gushing out. So what just happened? Well, the air expanded. This is a property of air. When air is heated, it expands. Likewise, when air is cooled, it contracts. Now, these properties of air is really what makes it interesting to be up at summits like this. It's hard to guess really what you're going to run into. But one of the important things that we need to realize about this air system is that it's working with convection. So when we're up here at these elevations, we need to time where we're going to be dependent off of what the conditions are going to be, okay? So what I mean by that is, say it's early in the morning, okay? The air's been stagnant all night. The sun hasn't been heating anything. Come the sun, the lowlands are going to start catching a lot of heat. Now, as that heat starts gushing up into the air, it's going to float high up into the atmosphere until it cools down. And then it's going to start ripping down onto the sides of the valleys. Okay? What I'm talking about is called convection. Now, convection is really important. Okay? Convection is really what makes everything go. It's very similar to what's happening over the oceans with the water cycle. Okay? And when we're talking about an ecosystem, as to what is going to influence an ecosystem, wind is huge. Wind is massive, especially at this elevation. Now, if you see where I am sitting right here, you might notice there's no trees. And you might notice it's really windy. Okay? It's really hard for anything to grow in those kind of conditions when the wind is just howling. So, when we're in mountainous regions, like I am here, that wind is very influential on what can grow in certain locations. Now, if you remember when we were looking out down below as well, if you looked out into the valley out there, there aren't any trees. Now, those lowlands are sometimes just as harsh as these high areas. And as this convection is ripping the air around and past the summits, it leaves a little bit of area right between the summit and the lowland. Now, if you did the pre-activity, you're going to recognize when I say elevation diversity gradient. Okay? We're going to talk about that in a little bit. We've got a little graphic here for you guys. We're going to talk about convection just a bit. Okay? So this is really what's happening when we're looking at convection. All right? I'm going to give you guys just a second. See if you can't see that. Okay? So we're seeing that the sun's heat is heating up the air in those bottom draws. It's making all of that air rise up high, way above where I am. I'm talking thousands of feet in the air, maybe 20, 30,000 feet up. Once that air gets up there, it's ridiculously cold. That air cools, it comes shooting back down, and we get a lot of wind here on the summits as it comes in. Now, not all wind is convection, okay? There is prevailing wind that's coming from systems, right? If you look behind me too, clouds. Those cirrus clouds are indicators of high wind. So summits not only are battered by convection winds, they're also battered by prevailing winds. It's pretty harsh up here. So as the air comes up, it gets hot, it expands, it stretches out. Another thing happens as we start gaining elevation. And now you guys might realize that it happens when you're driving a car and you go over a pass. What happens to your ears? Enter in the chat, what do you think happens to air, not only as it rises, but say when you go down too? What are other properties of air that changes with elevation? Let's see if we can get this chat to work. Okay. Well, I wish the chat was working. People are telling me it's working, but it's not showing up on my screen. So I'm just going to guess that probably one of you had guessed that the air expands. Not only does it expand, but the molecules move farther apart to the point that the oxygen and the pressure within the air is lower. Because the pressure is lower, all of the oxygen molecules and nitrogen molecules aren't as jam-packed together. So they spread out. They're like, ooh, we got all this extra room. We're stretching, right? That's great for the air molecules, but it's not great for us oxygen breathers. When you're trying to breathe oxygen at 10,000 feet, there's 30% less oxygen at this altitude than there is at sea level. So I might need to catch my breath every once in a while. I'm not used to these elevations. Now I want to share a little bit of a story with you. At one point, I was a little bit younger, I thought it'd be really cool to go up to about 14,000 feet. Well, I went from about 6,000 feet to 14,000 feet in a couple of hours. I brought all of my camping stuff, everything. I was laid out on this beautiful summit, perfect conditions, and I laid there all night, gasping for air. I seriously couldn't sleep. My heart rate couldn't drop low enough, my breathing rate couldn't drop low enough to induce sleep. So that's something to consider when we're coming up to elevations like this. Now we're going to start talking a little bit more about ecosystems, right? We're really covering kind of the basics as to what's happening up at these elevations. How can animals handle such low oxygen content, right? So we're thinking, what kind of animals, for one, are up here? Well, the obvious might be birds. Yeah, birds are really, really good at this. Birds can fly insanely high. Now there's one bird in particular that takes the cake for the highest. It's called Ruppel's vulture. Ruppel's vulture is an African vulture that can soar up to 37,000 feet. Have you ever been in an airplane? That's higher than your airplane's flying. So you kind of have to wonder, for one, what is the animal doing up there? And two, how did it get that high and how can it survive? How can it breathe? Well, animals are amazing, for one, and they adapt to handle these certain situations. And in fact, people even have adapted to handle high altitudes as well. Certain populations in the Himalayas, as well as in the Andes, actually develop a slight, I won't want to call it a form of dwarfism, but they have shorter limbs. That's because their heart doesn't need to work as hard to circulate the blood all the way out to their limbs. These people have been living in these mountains for thousands of years. Their bodies have naturally adapted to handle their environment. Kind of crazy. Okay, so we talked a little bit about how pressure changes when we're coming up to different atmospheres. We do it higher in the atmosphere. And I brought a can of seltzer just to show you. Now down below, you might have a can of seltzer and you could squeeze it a little bit. Well, this one, I don't know if you can hear it. It's really hard. The pressure inside this can is probably equal to what it would be if you had shaken it up down at sea level, right? But instead, it's just pressurized because of the difference in pressure. There's 30% less pressure where I am as opposed to where there is at sea level, okay? Now you can imagine, when we're talking about atmospheric pressure, right? Pressure is measured in two different things. There's PSI, pounds per square inch, and kilopascals. Kilopascals is much more scientific, so we're just gonna focus on pounds per square inch, okay? So, at sea level, you have about 14 PSI, okay? Here, where I am, there's about 10 PSI. And if you did the pre-activity, you'll notice as we go higher and higher and higher, it just completely diminishes into the point that there's only about, 50% of the oxygen that there is at sea level. That's not going to work for people like us that need oxygen. It just won't. So this is why people that go up to Everest need to have something to help them breathe. Okay? Certain animals have adapted that they can handle these sort of differences, but for us, not going to work. So here, at sea level, imagine, let's take my hand. It's about 4 inches wide, it's about 8 inches tall, okay? That's about 32 square inches. Now for each square inch at sea level, there's roughly 14 pounds of pressure pushing down on my hand. Now because we're in an atmosphere, there's also pressure pushing up on my hand too and on the side. But let's just pretend that that pressure doesn't exist, and we're just focusing on the pressure that's coming straight down. Well, out of the 32 square inches, I would be holding up about 450 pounds of air. So if you think about it, that's how the column of air that is above your hand. With the whole atmospheric pressure, doesn't really matter so much, but just to kind of visualize how much pressure there really is. We're just so used to it. It's kind of like fish at the bottom of the ocean. They can handle that kind of pressure because they're adapted for it. If you've ever swum to the bottom of a swimming pool, you might notice how much pressure is within your ears in a matter of feet just going down. Kind of fascinating. All right. So like I was saying, at 10,000 feet, 10 PSI, you could do the math there. We'd be looking at 320 pounds. So the difference between the 320 pounds in my hand versus the 450 down at sea level, it's just a good way to kind of visualize how different the pressure really is. Okay, I have more questions for you, but I really can't see what's coming through the chat. I know people are chatting away, so I appreciate it. I hope you guys can communicate amongst yourselves. I'm just glad that you can see me. So, we covered a lot of the nitty-gritty. So now you know about pressure, you know about the oxygen content, you know about the wind, right? Let's take a break and let's go cruise around and see if we can't check out the environment that we're at. While we are cruising around, I want you to enter in the chat. What exactly do you see? What do you notice about the environment? And now what I want you to pay attention to are the kind of plants that you see. I want you to pay attention to where the plants are growing. And then also pay attention to any other weird, I don't know, things you might notice. Erosion, things that are dead. Let's take a look. All right. So if you can tell, hope you can hear me here, it was a lot less windy where I was sitting. So I was on the leeward side of the hill just to get out of the exposure to the wind. All right, I'll give you guys a little bit of orientation. Right now we are looking west. This is north. Over that way would be east. And now we're looking south. So this is the south face of the mountain. Okay, very barren. We are above the tree line right now. We're going to talk about that in a little bit. Okay, and now we're looking on the north side. Now if we pay attention to the prevailing wind, it's coming out of the west here. Okay,